In this video, we are going to be discussing the topics in Chapter 11, which is our introduction to organic chemistry. So let's first introduce what is organic chemistry. Organic chemistry is going to be the discipline in which we look at the chemistry around the carbon atom. So the main element that we are going to be concerned with is carbon. Now, organic compounds themselves are going to contain carbon, and in addition, we're going to see carbon atom bonded with other nonmetals, including hydrogen, oxygen, sulfur, nitrogen, phosphorus, and even halogens. You may wonder why organic compounds are so important. It's because we have them in many products that we use in everyday life, including gasoline, medicine, shampoos, plastics, and perfume. Whenever the chemical formula for an organic compound is written, understand that the first atom that will be showing up is carbon. As we have seen previously, we're going to have a subscript to tell us how many carbon atoms are there. And then we're going to be writing hydrogen and any other element that is present in our chemical formula. The drawing that you see to the right of the slide, was made by a cartoonist which created mystical characters for each element of the periodic table, and this is the one that was developed for carbon. When we are studying organic chemistry, we need to first talk about functional groups. And functional groups are going to be a specific attachment of atoms that we're going to give it a name. As we discuss these topics in organic chemistry, we're going to see that identification of functional group and recognition of these functional groups is going to be crucial to understanding the chemistries that we are going to be discussing in these chapters. So let's first recognize that these functional groups are going to be composed of different families, and those different families, understand, that are going to be given by those circles that we have in the functional group. Another thing that I want to specify is that you may see that many of these functional groups contain an R, and R stands for rest of molecule. In rest of molecule, understand that at times means carbon atoms, and at times is going to mean hydrogen atoms. So I will specify when an R is going to be carbon with hydrogens or just hydrogen by itself. So let's first talk about the different families when it comes to functional groups, starting with hydrocarbons. As the name suggests, hydrocarbons are going to be compounds that contain just carbon and hydrogen atoms in their chemical formulas. So as you can see, when it comes to the members of the hydrocarbon family, that includes alkanes, alkenes, alkynes, and even though it is not shown here, I want to specify that the aromatic compound arene, which I'm now writing a red circle around, is also part of the family of hydrocarbons. Now, what makes each of these members different from each other? Well, in the case of alkanes, I'm going to highlight the atoms that make an alkane what it is. So for alkanes, we're going to have carbon-carbon single bonds and carbon-hydrogen single bonds. In the case of an alkene, we're going to have one or more carbon-carbon double bonds. And the R groups in that alkene can be hydrogens, also in the alkane. When we have an alkyne, that compound needs to have at least one or more carbon-carbon triple bonds. When it comes to the aromatics, or in other words, arenes, understand that they must have a hexagon that has alternating double bond, single bond, double bond, single bond, double bond, single bond, in that order. So whenever you see that motif, that is considered an arene. Now, going right along. The next one is the simple oxygen heteroatomics. Okay? What that means is that they're going to have oxygen. So in other words, to translate that, that is going to be oxygen containing compounds. So out of that family, we have two groups, an alcohol and ethers. So in the case of an alcohol, the R group is going to be carbon with hydrogens. So you need to have a carbon atom in which is bonded to an OH in order to have an alcohol. In the case of an ether, R1 and R2 are going to be carbons with hydrogens, which means that an ether is going to have an oxygen bonded with carbons on either side. The next group that we have are the halogen heteroatomics. This just means that we're going to have halogens in the molecule, and the only member of that group are going to be haloalkanes. And in general, these are going to be halo hydrocarbons because they can be present in alkanes, alkenes, alkynes, and even arenes. The important thing that you should know is that that R group is carbon with hydrogens. And again, the number of carbons can be unlimited, and the number of hydrogens, as long as carbon has 4 bonds, that's pretty much it. But we will discuss that further as we progress in this chapter. The next group that we have is going to be carbonyl compounds. And when it comes to carbonyls, we have 5 members of that family. We have aldehydes, ketones, carboxylic acids, esters, and amides. So, when it comes to this, understand that what makes them be part of the carbonyl family is because they contain an oxygen double bonded to carbon. Now, understand that in order for us to have an aldehyde, which is the first member, that C double bond O has to be single bonded to hydrogen on one side. The other side, so the R group here can be hydrogen or carbon with hydrogens. In order to have a ketone, on each side of that carbonyl, R1 and R2 need to be carbon with hydrogens. If we have a carboxylic acid, you must have to one side of that C double bond O an OH. And then the R group in that carboxylic acid can be hydrogen, or it can be carbon with hydrogens. In order to have an ester, we need a single bond to oxygen, and that oxygen must be bonded to an R group, and that R group must be carbon. So R1 can be hydrogen or carbon with hydrogens. That R2 must be carbon with hydrogens. When it comes to an amide, that carbonyl group must be bonded to a nitrogen. And that nitrogen, as you can see, it can be fully covered with hydrogens. And then remember that the common bonding pattern for nitrogen is 3 bonds and 1 lone pair. That's why it is illustrating just having 2 hydrogens. But if that nitrogen has carbon with hydrogens, that's fine. The R group in our amide can be hydrogen or carbon with hydrogens. And our last group, in terms of the compounds that we have to identify, is going to be nitrogen-based organic compounds. And here we have amines. And when it comes to an amine, understand that R group has to be carbon with hydrogens, because if the R group is hydrogen, then we're going to have ammonia. And in fact, amines are derivative of ammonia. One of the functional groups that you don't see here but is part of the system, when it comes to the sulfur-based compounds, if we have an R group that is bonded to SH, that is called a thiol group. And in thiol, that R is going to be carbon with hydrogens. So to practice the recognition of functional groups, you must be able, for the next exam, to, given an organic compound, identify the different functional groups. So if we go to part A on our chapter 11 worksheet, you can see that there's two molecules. On the top, we have capsaicin, and capsaicin is going to be a compound that is present in spicy chili peppers. And depending on the amount of capsaicin, that's how much spiciness our body can detect. And in the bottom molecule, that is vanillin, which is what gives the flavor of vanilla. So let's first identify the different functional groups that are going to be present in capsaicin. One of the things that I should specify, and we're going to learn as we learn the structures of these compounds, is that when it comes to the arenes, each corner of an arene is going to have carbon atoms. So the reason why I want to write them in is because right now it may not be so obvious certain functional groups that we have in the system. So let's get started with identifying the different functional groups that we have here. I'm going to be highlighting all of them in a purple color. So starting from the molecule, starting on the left. Remember, every time we have a carbon atom bonded to OH, that is known as an alcohol. This hexagon that has alternating double bonds and single bonds is what we know as an arene. When we have a carbon single bonded to oxygen, that oxygen single bonded to carbon, that is known as an ether. If we have a carbonyl that is bonded to nitrogen and that nitrogen contains carbons and hydrogens, that is known as an amide. If we have a carbon-carbon double bond, that is known as an alkene. Understand that when you have carbon, and carbon, hydrogen single bonds, even though we identified those as alkanes, in the context of a larger organic molecules, alkanes are not going to be part of the functional groups that we identify. Let's move on to the molecule of vanillin. So I'm going to write in the carbon atoms found in the hexagon. And let's identify the functional groups present. As we learned in the previous slide, a carbonyl that to one side has a hydrogen, that is known as an aldehyde. If we have that hexagon that has alternating double bonds and single bonds, that is known as an arene. If we have carbon single bonded to oxygen, oxygen single bonded to carbon, that is known as an ether. And if we have a carbon atom holding an OH group, that is known as an alcohol. Let's now learn the properties of organic compounds. Understand that when we're talking about organic compounds, these are going to be covalent compounds because they contain covalent bonds. Organic compounds have low melting and boiling points. They are flammable and they undergo combustion reactions. They are not going to be soluble in water, so that means that organic compounds are non-polar molecules. And as we learned in chapter 9, remember that like dissolves like. So the reason why vegetable oil, which is a non-polar compound, which is also an organic compound, doesn't mix with water is because it is a non-polar compound. Now, the first thing that we're going to be learning in this chapter is the first member of the hydrocarbon family, which is an alkane. So remember, alkanes are going to be hydrocarbons that contain only carbon-carbon single bonds and carbon-hydrogen single bonds, okay? So when it comes to alkanes, understand that they have the general chemical formula CnH2n plus 2. So what that means is that if we have a hydrocarbon, its chemical formula is going to fit that structure or that general formula. So for example, if n equals 1, which is just a value, as you can see, C1H2 times 1 plus 2 is going to give you the chemical formula CH4, which is the simplest alkane. As you can see, alkanes are formed by continuous chains of carbon atoms. Now we are going to be learning how to name these organic compounds based on the IUPAC system, which stands for the International Union of Pure and Applied Chemistry. And one of the key features for alkanes is that we will see that all of the names are going to end in "ane." When it comes to naming compounds in organic chemistry, is more systematic than what we have observed in inorganic chemistry, which is the chapters that we were discussing before. They're going to have a very systematic, meaning that you will see how the functional groups is very related to the name. And as you can see, we use Greek prefixes to determine the name of the carbon chains with 5 or more carbon atoms. So, as you can see, table 11.2 on your textbook tells you the names of the first 10 alkanes. The main thing that you guys need to do when it comes to this table is to memorize the number of carbon atoms and the prefix that they correspond to. So it is essential in organic chemistry that you're able to do this. So again, memorize the number of carbon atoms and the prefix that they correspond to. So as you can see, if your alkane has 1 carbon, then the prefix is meth, and because it is an alkane, we're going to call it methane. 2 carbon atoms is going to be eth, so we have ethane. 3 carbon atoms is prop, so that's how we have a propane. 4 carbon atoms is bute, that's why we have butane. And then 5 through 10, we have Greek prefixes: pent, hex, hept, oct, non, dec. And because these are alkanes, we have pentane, hexane, heptane, octane, nonane, decane. So make sure that you memorize the number of carbons and the prefix that they correspond to, because this is going to be crucial for naming all the organic functional groups that we will be discussing this semester. Now, there are different ways in which represent alkanes, okay? So we can have the alkane name, and we're going to be exploring that further in this chapter. And before, we were doing molecular formulas for compounds. We are going to graduate from molecular formulas. We're going to find new ways in which we're going to be drawing these compounds. As you can see, we have the ball and stick model. And when it comes to the ball and stick model, this is based on those model kits that we utilized in the laboratory in order to identify the compounds. We won't be using those this semester. Now, understand that when it comes to the expanded structural formula, this is going to be like those Lewis structures that we explored previously. They are calling expanded formula because you can see the carbon atoms, and you can see, in this case, because we're dealing with hydrocarbons, the hydrogens that are bonded to. I need to specify that when it comes to carbon can only have 1, 2, 3, 4 bonds. Carbon does not have an expanded octet. So we always have 4 bonds to carbon. Now, when it comes to the condensed formula, understand that the condensed formula, when we compare it to the expanded formula, is going to be when we include or we bring in the hydrogens. So, as you can see here in this molecule that is hexane, because it contains 1, 2, 3, 4, 5, 6 carbons. What is going to be occurring is that I'm just going to highlight the atoms. The first carbon, carbon 1, is bonded to 1 hydrogen, 2 hydrogens, 3 hydrogens. That's why it becomes a CH3. I'm going to now number the carbons so it makes more sense. Carbon number 2 is bonded to 1, 2 hydrogens. That's why it becomes a CH2. The same thing is going to happen with carbon 3, carbon 4, carbon 5. They are all CH2s. And as you can see, carbon 6 is bonded to 1, 2, 3 carbons. That's why it becomes a CH3. Now, understand that a CH3 can be written in that manner, but CH3, if it's bonded this way, or if you see a bonded when it's H3C, these two ways of writing it mean the same thing. And then the last way in which we can write these structures is by doing the skeletal formula. When it comes to the skeletal formula, this is known as the line angle formula. So understand that the line angle formula, here we are going to be representing carbons and hydrogens, but they're going to be implied, they're not going to be written in the molecule. So the best way to know how to write the skeletal formula is by the minute that your writing utensil touches the paper, you're going to write a circle, and that's going to be carbon 1. And then, because each one of these carbon atoms are tetrahedral, as we move up and down, that is going to be symbolizing another carbon atom. So if this is carbon 1, this is carbon 2, this is carbon 3, carbon 4, carbon 5, carbon 6. So we have 1, 2, 3, 4, 5, 6 carbons. We are going to be practicing more on how to draw these molecules throughout this chapter.